A fresh cup of coffee. It's a great way to start a day. But as I sit and look at it, I wonder, why doesn't it stay hot? If I put a room temperature cup of liquid, it would stay room temperature. But making a hot cup of coffee, it only achieves optimum heat, temperature, drinkability at a very certain level, and then it cools off. And then coffee's cold and rather gross. Why does the heat leave? Why doesn't it just stay put? Why is it always trying to move away? Well, the reason is heat literally is movement. When I take the molecules of water that are room temperature and I put them in my kettle, I add electricity to it, and that increases the vibrations of the molecules, or the kinetic energy, the movement of the molecules, and they start to shake. And the more they shake, the hotter they get. And when I put them in this cup of coffee, they're shaking, vibrating at a high level. That's why they're hot. But that vibration is movement. And right now, that movement is causing collisions between the molecules of the water and the molecules of the cup. And the molecules of the cup are starting to vibrate more and more as they're getting hit by the bouncing around molecules, the super hot molecules of the water. They're starting, and so each collision spreads heat and slows down the initial particle or molecule. So it's spreading that way. It's also spreading, if you could see this, by steam, which is a form of convection. So as it's vibrating, the air around it is not vibrating as much. So these ones start moving up to the top. They shake their way up. That's convection. And then there's one called radiation. And I can put my cold hands up against, close to the, not touching it, because then that would be conduction, where things are actually touching and bouncing into each other. Radiation is when I can feel the heat from far away. I can blow. You can feel the heat. But the heat is radiating through the electromagnetic field, just like this light. And the light, I can feel the heat coming off the light as well. That's radiation. And so through all these ways, heat is moving away from this delicious cup of coffee. So I better not wait anymore. Cold does not exist. Heat is a measure of the kinetic energy, the movement or vibration of molecules. The hotter a substance, such as water or steel, the greater the kinetic energy, the movement or vibrations of the molecules in that substance. Less hot objects, sometimes called cold, have molecules with less kinetic energy or those movements or vibrations. Thus, objects and substances are not cold and do not get cold. They always contain a measure of heat, and they get less hot. So in my jug here, I do not have a refreshing iced beverage. I have a refreshing, less hot beverage. I prefer as less hot a beverage as I can get, all the way through slushy, right to the brink of frozen solid. However, consider this. Even water in the form of an ice cube still contains heat. The molecules of water in ice still vibrate, just far less vigorously than liquid water molecules, or heated up coffee molecules which vibrate with gusto. So here's the question: how less hot can you go? Absolute zero is the lowest limit of the thermodynamic temperature scale. Thermodynamic, you remember, means heat movement. So absolute zero is a state at which enthalpy and entropy cease or reach their minimum values, which means the molecules stop shaking. The fundamental particles of nature have minimum vibrational motion, but you can get very close to zero. It's very, very difficult to get all the way to zero where movement stops. And this is absolute zero. So heat in the form of kinetic energy or movement or vibrations flows from hot to cold objects, because as the molecules move, they share this kinetic energy with other molecules through collisions. Hot water molecules bump against the molecules of a coffee cup, increasing the vibrations in the molecules of the cup. This transfer of energy will continue until the system reaches a state called thermal equilibrium, where both objects are the same temperature or have the same average heat in their system. And all the bumping around settles to match the environment surrounding it. So a room temperature cup of liquid becomes room temperature, which is a good description, by sharing all its excess kinetic energy with the room. And so the kinetic energy spreads out and everything in the room becomes uniform and they're all bumping each other without sharing any energy because they all have the same amount of energy. This is thermal equilibrium, and heat is always seeking this movement from high concentration to low concentration. Why does a hot cup of fluid get cold? The direction of heat from high concentration to low concentration is explained by the second law of thermodynamics, commonly simplified to the single term entropy. In the simplest terms possible, I could describe entropy as a universal tendency for an ordered system to gradually decline into a disordered non-system. So consider a beaker filled halfway with white jelly beans, and then carefully a second layer of red jelly beans is placed on top. From the initial stage, after the careful separation and organization of the system of jelly beans, they will inevitably become more mixed. That is the only direction they can move. They cannot become more organized. They only have one way to go. And if you were to pick up the beaker and shake it a little bit, the entropy would increase and they would mix faster. And the shaking of the beaker is similar to the kinetic energy of heat in molecules. They're already shaking. And the more heat, the more shaking. And thus the greater the mixing of the jelly beans. Or the mixing between hot liquid and a cold room around it. You're shaking those two heats together and they'll mix to combine into a equal heat vibration or thermal equilibrium. As with many other fundamental forces of the universe, such as gravity, we are so accustomed to living in a world that adheres to these laws that we can often fail to see them and fail to appreciate their majesty. So here are some examples of entropy to help you get a deeper understanding of how entropy is all around you. So number one, you clean up your bedroom and over time it becomes dirty again. Number 2, you pour yourself a hot cup of liquid, then forget about it. And when you come back to the cup of liquid, it's room temperature or cold. 3, you take a tour of the ruins of Rome. 4, you break an egg to cook an omelet. 5, you squirt Mio flavoring into your water and see it turn the water red. 6, you put the final touches on your hair and it is perfect. Then, by the time you get home from school, your hair is a mess. 7, you wear a hole through your sock. These are all examples of the everywhere presence and persistence of entropy. Dirty rooms do not over time become cleaner. Cups of cold coffee do not spontaneously become hot. And the buildings of Rome did not stay pristine, but have become ruins. Likewise, with the rest of the scenarios in which order devolves into disorder. Entropy is order to disorder. This is a fundamental reality of our universe. Unless you put in the work to create and maintain order, everything around you will relentlessly decline into chaos or disorder. When considering making things hot or cold, remember that heat is always moving toward thermal equilibrium. Attempting to make a substance or object hot or cold is very much like attempting to build a sandcastle or to dig a hole on a beach. Indeed, the higher or lower the temperature, the more vigorous the dissipation of that heat. Think about somehow achieving a very high sandcastle. Eventually, when it crashes, the crash will diffuse more energy. It'll release more heat. Dig a very deep hole, and the rate at which water from waves washing the walls of the hole down is likewise more vigorous. Making something very hot or very cold is an attempt to fight against entropy. And the farther you push against entropy, the more it pushes back. It grows in intensity. The colder you get a substance, the more likely that the sand around the hole will fall into the hole and fill it up. And the hotter you get a substance, the more likely it is to come crashing down. So if you're on the beach, you build this sand castle high up. And the higher you build it, the more likely it is it's going to fall eventually. And if you dig a hole, the deeper you dig the hole, the more likely the hole's going to collapse. And once you stop working to build the castle or dig the hole, they will both gradually and inevitably decline toward the perfect sea level, and the beach will appear as though you never existed. Now, before you think this is an overwhelmingly bleak idea, entropy, that it can wash away all your work and be like you never existed, and this is just a fundamental law of the universe, remember this. It's fun to build sandcastles on the beach. And on an episode of Friends, Joey's on the beach and he's digging a hole. And he's having a blast digging that hole. It's fun to play against entropy. Without entropy, the universe would be dead. It would be inert. There would be no movement, and nothing would or even could happen. Entropy, like gravity or electromagnetism or light, is simply one of the operations of the game. And once you understand this, you can start to play with it. Thus, I was able to melt copper and aluminum in my backyard. Thus, building a great structure of any type is a grand achievement. The structure you create is a monument to your victory and triumph against this eternal foe of entropy. Okay, here we are at the desk, the laboratory. I've brought two very concentrated forms of anti-entropy. We've added a lot of heat into this concentrated form of water. Heat-bearing water. I've heated it up, I believe, to about 190 degrees. And as we speak, it's losing energy, so we're losing concentration or order of heat into entropy as we speak. Over here I also have the removal of heat in an order called ice, where it's been removed, but heat is already, as we speak, transferring into that. I also have a thermometer to check our temperatures, or the average temperature of our systems. That says 60 degrees Fahrenheit, but we don't want Fahrenheit, I want Celsius. Let's see what the ice reads. So it's 6, 1. Very good. It's cold. It should be about 0 because that's when water freezes. So that's what we're looking at. Over here, let's see if we can. We'll put it onto the tin, or the outer covering the aluminum. 41 degrees. But let's point it onto the water directly and see. You can see some steam coming off. Alright, I got it on the water directly. 80, 90 degrees Celsius. And that's about right. It boils at about that temperature in Colorado because of the reduced pressure. So I have two containers here. I have the glass one with no insulation. It does have a top, which will slow down convection, which is the flow of heat, like the steam that came rising out of here. With the top, that'll slow down, but conduction should be going pretty well because of the glass. And then as the air passes the glass, you'll get some transfer of convection that way. Over here we have this incredible thermos where it has a container on the outside and then a container on the inside. And in between those two containers there's air, or a vacuum, which does not transmit heat. But these two containers may not touch down here in the body, but at the top or around the neck, they have to touch somewhere. It can't just be suspended there. So you'll get conduction from there. But I'm going to go ahead and pour this hot water in there. Same with this one. And I'm going to go ahead and put the yeah. Well, we already took the temperature. So now I'm going to go ahead and seal them up. And we're going to watch how a thermos is actually an anti-entropy tool as compared to a glass. Right there. So we'll go ahead and set those. We'll come back in a certain amount of time and check on them. Let's move over here towards the ice, which is, so if heat can be thought of as an added on feature. So imagine you're on a beach that's perfectly flat, and now adding heat to the system, you're building a sandcastle up on the beach. And as the waves come, it'll slowly wash it down, just like these super hot containers will slowly go back to the room temperature. Over here, when we talk about ice, it's like we've dug a hole on the beach. We've removed sand. We've removed heat. And so there's less vibration. There's less kinetic energy in the water, which is why it doesn't move. It's in a solid form. It's not moving like water does. It's less energetic. However, right now the temperature in the room is above the temperature in the ice, and so the temperature in the room is actually moving into the ice. However, there's ways we can increase or decrease the transfer of this energy. So when you go to Sonic, for instance, and you get an iced Route 44, it comes in a styrofoam cup because styrofoam does not transmit heat. And what we'll see is that some materials transmit heat. And unfortunately, you can't get the full effect of this demonstration because you can't touch these two materials. They're different. There's two materials. This one over here, it feels cold to the touch, where this one feels a little warm almost. It almost feels warm. And this one feels cold. And so when I put ice onto these two surfaces, what's going to happen? Well, they're going to transmit heat differently. And we'll see how that happens. So I'm going to pour some ice here. And I'm trying to hold the camera as I do that. Oh, I made a mess. And you can see right away something weird starts to happen. But we're going to watch the two different materials. And I'm going to come back as we watch how the transfer of heat affects this ice. The entropy increases, and it increases at various rates depending on what materials we're working with, or how we've buffered ourselves against this transmission of heat. All right, welcome back. Here we are. We see that the ice on this material has melted almost all the way down. And in fact, if I had removed the ring and the water was able to move, it probably would have melted all the way. And this one barely melted at all. And that has to do with the fact that they're different materials. This one's made out of aluminum. And it turns out aluminum is great at conducting heat. And so it conducts heat into the ice. And when you touch it and it feels cold, the aluminum by itself, that's because it's drawing heat out of your hand. Where this one feels kind of warm because it's not conducting heat. There's no heat transferring from my hand into the material or back and forth. And I forget what that material was. I think it was styrofoam. We'll check. I'll double check on that in just a second. But here we come back to our thermoses or our containers for heat. And we have this one that's not a thermos at all. It's just glass. So when I touch it, it's pretty warm. I can feel the heat in my hand. It's going into my hand, so it feels hot. And what about this one? A little bit of warmth. I feel a little bit of warmth, which means some heat is radiating into the outer part. I feel it on the lid a lot, which is interesting because that's where conduction can happen the most, and that's where convection wants to go. What about the lid of this one? Oh yeah, the lid's nice and warm. Okay, I'm gonna go ahead and open them up and put the thermometers in. Okay, we're back. I checked on it. This material is a plastic foam, which is, plastic isn't a good conductor of heat. Plus, a foam means they inject air into it, and air itself isn't a good conductor of heat. Air works in convection, but it doesn't conduct heat very well, which is what is going on in our thermos. There's a gap between the container holding the water and the outside shell, and that gap has air in it, so it doesn't conduct heat very well. Go back to our original water, and it is showing, let's see if I can get it into focus, about 55 degrees. And actually, that's what the gun was saying. Let's see. Yeah, it's kind of close. Huh. So we had about 55 from the normal. And then these are the two thermometers that don't actually have numbers on them. But I'm gonna try and pull them out and set them down, and we'll see how they compare to each other. There we go. And you can see, oh, I shouldn't turn the camera because that's not helpful. This one here is much lower. And that was the one in the glass, so more heat has been lost than the one in the thermos, which was on that side. And I don't know if this has any relation, but I don't know. Let's try and use the thermometer on each of the other two. I'll go ahead and try that, and well, it'll take a while. Well, it turned out not to have taken very long at all. Once I put it in there, that's about at 80, and then you can see it drops pretty quickly. That's really interesting. You're getting some heat transfer because of the water taking heat with it through evaporation, and just like when we sweat. And I don't know how long it'll take to establish the actual temperature of this one, because now the thermometer itself has to go through an equilibrium process, because I had put it into the hotter container and now it has to lose heat in order to get an accurate temperature reading on this one. But we'll say it's right about there at about, that's a good view. Oh, it went all red. There you go, 55. And then let's see if I can't show how quickly it rises. Oh, there it goes all the way up. I guess that's about it, 85. Anyway. Alright, so here we are. We have 3 containers. Now, we're going to pretend that this water is heat that I'm pouring into these containers, these systems. And we're going to watch how entropy, which is heat trying to seek its equilibrium, will find any way to escape a container. These are an analogy for how heat tries to escape containers, and how we can alter those containers to slow down the rate of heat escaping. So this is just a standard glass container, and I'm just going to turn the heat on at a decent low pace here, and we'll see what happens as I try to add heat to this system. Let's say like a pan on the stove perhaps, or a hot cup. You're adding tea to the cup, but the heat's leaving through the top of the cup, through convection, through the heat evaporating that way, through conduction, through it touching and being absorbed into the heat in maybe a spoon, and even from your hand touching it, you're sucking some heat out. It's losing too much heat, and very quickly it'll lose its whole heat, and you'll have a cold cup of tea. So what if you use like a nice insulated cup, styrofoam cup, which lets out heat very slowly? You can hold the heat much more effectively. Not only can you fill it with more heat to begin with, I suppose, but that heat dissipates much slower. We've got this styrofoam insulation, which means less holes, and see there on the bottom there. But with the lid on top, you're lowering the rate of convection loss, because the styrofoam doesn't conduct heat. It can store heat very well, and that's why you use styrofoam. And a thermos. Thermoses are like that with even less holes. But let's imagine a perfectly sealed off container, which is essentially impossible. You cannot stop heat from finding an escape. It will always find an escape. But if you could fill your system with heat, and the heat would remain there. And we'll see that. In a very short period of time, the heat has left these two systems. And this can be equated to our backyard furnace over here. It was more like this. So many holes in the system. Heat coming out of the top. Heat going through conduction through the furnace itself. Heat radiating out. You could see the light as it was getting hotter. If we had had a system that was perfectly closed, or even more insulated, actually I guess this would be like a fire pit, and our furnace would be more like this, where it's kind of insulated. That's what the furnace itself is. And then if we could somehow have a perfect system, we would only have to add a certain amount of heat. And then it's too hard to even imagine, because there is no such thing as a perfectly sealed off container. Anyway, this was our demonstration of different containers attempting to hold heat, and how heat will find ways of escaping. Understanding that heat is movement, we can ask the question, how does heat move? There are three primary ways. Conduction. This is when heat is transferred through direct contact, as observed when heating a pan to cook food, or placing a spoon in a hot cup of tea and the spoon heating up. Convection. Convection is the circular motion that happens when warmer air or liquid, which has faster moving molecules making it less dense, rises, while the cooler air or liquid drops down. This can be observed in the rising heat of a candle causing a spiral of aluminum foil to rotate, or the food in an oven being cooked by the circulating heat in the air. Radiation. Radiation is energy that is radiated or transmitted in the form of electromagnetic waves, such as light or microwaves. A microwave literally shakes the molecules of food, causing the temperature of your burrito to increase. The energy of light, for example, can be observed in the varied internal temperatures of a black container with water versus a reflective container left in the sun. Through these three methods of transfer, heat is nearly impossible to contain or resist. Consider a thermos with hot liquid. The design decreases the rate of heat transfer, but does not stop it. When we used our backyard furnace to melt copper and aluminum, much of the struggle was against entropy, as most of the heat generated by burning propane was lost through 1. Conduction, the heat moving from the furnace to the ground; 2. Convection, the heat rising out of the top of the furnace as exhaust; 3. The radiation as seen as the light of the glowing orange furnace itself, or the crucible. However, at a very concentrated point in the center of the crucible, in the form of the atoms of copper and aluminum, we were able to focus enough energy, enough heat, to reach the melting points of those metals. If we were able to view the process with a thermal lens, we would see a giant cloud of heat with a tiny point of high intensity at the center. Our little backyard furnace is hardly a sufficient container for heat. Another way to think about this is to go back to the beach. Reaching the melting point of copper is like having built a giant mound of sand that allowed us to place a flag about 100 feet above sea level. It would take a giant pyramid of sand to reach the height of 100 feet at only just this tiny little apex. And now our backyard is cool. The furnace is in the shed and the metal is frozen. And likewise, on the beach, this giant mound is washed smooth again, and the beach is smooth as far as you can see. So thinking about building a mound of sand on a beach to reach a higher and higher temperature, melting points of copper, for example, the question you can ask is, how hot can it get? And there's a link that you can follow and answer that question. Right now, we're going to look at each of these methods individually. And we'll start off with conduction, which is the transfer of heat from one substance to another by direct contact. Here I have a device that'll show us how different metals conduct heat. I'm going to place it in a vise, and we're going to put a candle under the center of this, I don't know what you would call it, but it has different pieces of metal pronging outward. And we're heating up the center, and we'll see how well each of these different metals conducts heat toward the outside. And we've placed butter on there, so you can see it's starting to melt off. And it melted off 3 of them already, but 5 of them, or 2 of them still have it. So, and I'm trying to use the laser to get a heat reading, and you can get good heat readings. It's not always the best because it's hard to hold the laser and look at the
I'm gonna touch this one.
temperature screen.
No problem. I can feel the heat here, but when I touch this, it's really hot. Ah! Not so hot. Pretty hot. Woo! Very hot. Wait, give it a shot. Try this one first. Slow down. What are you doing? Give us some feedback here. Try this one again.
Smoking hot.
Okay.
This is cool.
Hold this one for a second to show everybody you can. Okay, now try this one again. That's copper.
That's hot.
Okay.
That's pretty hot too.
This one's the hottest one, dude.
Oh, each.
So touch the cold
Butter?
one. Oh, it melted off. Look.
That was me. I touched it.
Oh,
I
it's
saw
so
it, but I
hot.
touched it.
Okay, now try this one.
And this one. Hot.
Which one's hottest?
This one.
This one, by far, right? Burns you right away.
Then this one. Then this one. And this one and that one. Ah! Look at these pens. What are called pens?
So in a perfectly Baconian, hands-on, through actual observation and experience, we're able to see that heat transfers through different metals at different rates. And we can zoom into the middle of this device and see that there's little letters, and each one of them indicates what the metal is. So we'll start at the left, and here we have steel. Then we go to a B, which is for brass. And then we have one straight out of the top, which is A, which is for aluminum, which turns out to be the hottest one, which is very interesting because it melted the ice very quickly, if you remember previously, or it was involved in the melting of the ice. It transmits heat very effectively. Next we have stainless steel, and finally over here we have copper. And they all were able to melt the butter at different rates, and you could touch them depending on how hot they got. It was a very great experience. But aluminum seems to be very effective at transmitting heat. Very interesting. Next, we're going to look at convection, which is the transfer of heat through a fluid, such as a liquid or a gas. As we learn about entropy, we're learning about how heat travels, how it moves. It's energized particles, and they're shaking around, and they're constantly moving about. And so today's demonstration, what you'll need is something to start a fire, a piece of aluminum foil, about 12 inches by 12 inches is more than enough. You'll need some scissors, a nice long pencil, fresh pencil, sharpened, or a kebab stick if you have one of those. Either one will work. We're going to try them both. You'll want a marker. That's not necessary, but you could have it with you. Next, this one's kind of hard sometimes. You need a candle, and then I've cut out a little piece of cardboard to collect the wax, because we're going to get some wax spillage and you want something to collect it on. Alright, so what we're going to do first is we're going to go ahead and light our candle, because we're going to need it to heat up the wax, and because we're going to need some wax. We're also going to need the candle for other things, but we're going to just light that up and we'll set that aside. And let's see if I adjust the light. Is it better like that? Or like that? I like that. I'm going to leave it there. Okay, next we're going to set these aside. We didn't need the matches. I don't like striking a match inside because it smells. With our marker, what we're going to do is we're going to look at the center of our piece of foil, and mine just happens to have a crease in the middle here, so that's about my center point. And I'm going to put basically a circle there. But out from that circle, I'm going to draw a spiral. And I want to keep the arms of the spiral relatively equal to each other. And there we go. So I have 1, 2, 3 arms of a spiral, and I think that's probably more than enough. Now I'm going to go ahead and cut this out.
Here I have a circle. Now I will cut my spiral.
All right, very good. We've cut our spiral aluminum, and it actually looks like we're not going to need nearly this much. So I'm going to cut off about a little, I don't know, I'd say 1/4 of it at least. And so I'll leave my spiral off to the side right now. We're not going to be dealing with that, so I'll put that off to the side. We'll bring back our candle. And at this point, let me see if I turn off the light, if that kind of affects how you can see the... No? All right. Well, I have a candle. You can't really tell that it's lit, but it's got some wax in it. And now what we need to do is I need to use that wax. I need to pour it out because I need to stick this pencil or this kebab stick. And I'll actually use the kebab stick first. It's longer, which is good for the spacing we need, but it's also lighter. But if you don't have a kebab stick, you would use a pencil, and I'll try that one and see if it actually works. So what I'll do is I'm gonna, I don't know, I'm gonna try and lead the wax out one of the sides here. Let's see if I bring it closer, maybe. Don't burn your camera. Wait. Let's see if I turn off the light now. Nope, you still really can't see the flame. All right, well, I'm gonna pour the wax. I've created this moat, or this kind of funnel part. I'm gonna pour the wax down that and try and get it onto the stick and also onto the board, although it would have been better if I had it in the middle. But I need it to be on the stick, and I need to work that stick into the wax. Oh, okay. Let's go a little more wax. And I guess what I could do here is blow out the candle, because I still have the hot wax working, which is what I need, because I need it to hold the stick in place. So we're pouring the wax, we're trying to get the candle or the kebab stick to stay in place. And that looks like it might work. All right, and it's actually at a kind of angle, which is good, because the point of the stick is going to be right over the flame. So I'm going to go ahead and let that dry for a few minutes. Or not dry, but return to its frozen structure, which is a freezing point. So it's got to cool down and reach its freezing point, the wax. All right, so we're back, and I've let the wax solidify, and I'm going to set that off just to the side a little bit as we move back to our spiral of aluminum foil. Now what you're going to do with the aluminum foil is we're going to try and make an apex, a point where the circle was, where we can rest it on the point of the kebab stick. And the goal of doing this, and I'll show a different view here, is to allow it to spin freely. Here we are looking at it from the side, and you can see it can spin freely. It's not touching the stick in the middle. You might have to make adjustments so that it's not rubbing up against the stick in the middle, which will slow its ability to rotate. All right, so at this point you should have your stick firmly attached to the candle thanks to the solidified wax at the bottom. You have a coil or a spiral of aluminum foil that spins freely without rubbing up against the stick in the middle itself. And then you're going to have to remove your spiral because we have to relight the candle. And this is where having a match might come in, because I'm going to have to bend this in a weird way and the candle's going to want to move. And I don't know if I can get it with a lighter. Oh, I did. Okay, good. I was going to use a match because I could get in at a different angle. But fire goes up and it'll burn you either way. Okay, so here we go. We have our candle lit once again. And now we'll replace our aluminum foil. We'll go from the top and drop it in right on the center of the kebab stick. And the heat from the candle, heat being energized particles shaking around in the environment around us, are moving up. So they're shaking themselves up in the cool air. Oi! That'll happen. You can readjust. There we go. And then I have the fan in the house on, so that's going to affect it. And I'll have to turn that off to see. But so these heated particles are shaking up and they're pushing up against the aluminum foil. Okay, one more thing I wanted to try just while I have the candle burning and everything set. And I'm going to try the pencil in just a minute and see if I can't get this pencil stuck in place, if that's a possibility. But I want to try going smaller. My last spiral was really big, and I want to try and be more efficient. And so I'm going to try and make my spiral smaller. And I don't think it needs to be that long. Although, see, I'm weaving, so when I cut it, I'm going to have to take into account those weaving and try and adjust on the cut. So I'm just cutting out the big shape, and then I'll go and do some detailed cutting work as needed. But it doesn't need to be perfect, although the more precise you are in your cutting at this stage, the more likely you are to get a good spiral going. So I'm just going to start the spiral and come in, and this will take me just a minute. Okay, I've cut my spiral. It turns out that the one I drew onto the paper with, or the aluminum foil with the marker, didn't have anything to do with what I actually cut out. It actually just kind of got in the way. And I didn't need nearly as much as I have, so I'm going to cut some off there. Oh, now I cut it too short actually, but I have some extra space. And in order to make the spiral more precise, I'll just kind of run my finger along it here to try and get it going in a nice smooth motion, because there's a lot of wrinkles in it. Oy. Oh, and I just ripped it. This is really fragile stuff. Alright, let me stretch it out just a touch and we'll put it on here and see if we get anything going. Oh, nice. Okay, good. So as I was putting it on there, I can actually feel the heat rising. And we seem to know this just from common experience, where you go to a fire, you put your hands up above it because that's where more of the heat goes. And in the winter, when you turn on the heater, the air may come out of the vents on the floor, but the heat will rise to the ceiling. And so even though your thermometer may turn off, the temperature variations in your home or where you're living will vary depending on if you're upstairs or downstairs in the basement. Heat shakes, so it'll rise to the top. It's if you put all this heat, all these different heats in, the hot air will shake up to the top, and it'll actually disperse out as well. So, but we can see heat is definitely rising. Okay, so the lighter you go, the more energetic the spin. That's a good. This kind of would attach to the flight the principles of flight. You're getting a fluid moving over. You would want a foil shaped, not made out of aluminum foil, but the foil, the shape of a wing. And it would probably be better if it was much longer. So maybe I should have tried that. I should have gone much longer. There's a lot of variations you could try. You could try thicker spiral. That would create more surface area, which might create more spiral. It would capture more of the heat. A lot of the heat's just coming up out of the sides here. I can kind of feel it. There's like I can feel it in my hands here. Let's see if I can close it a little. And funnel the air up. Oh yeah, look at that. I'm kind of channeling the hot air rising from the candle with my hands. Let's see if I remove it. Well, that's still going pretty good. Maybe it's kind of found a vortex of sorts just by giving it a little direction. And that's going well. Now let's try, in case you don't have a kebab stick, because who has kebab sticks? I have them because I'm just planning on doing stuff like this. I have kebab sticks in a big jar or a big bucket. I have a lot of stuff. But let's try and stick a pencil with the wax. So I'm going to go ahead and remove that. I'm going to break that off. It's got a little bit of wax on there. I can kind of use that as a primer here. But remember, you want to dig a channel. Oh, there's a big one. But I'm going to blow out the candle now. Pour the wax on the side of the pencil. See if I can't work the pencil in. And then pour the wax over the pencil. Gotta be careful. That wax is hot. It's like the heat from a hot glue gun. Okay, well, let's see if that sticks. All right, we're back. I've let it cool off. Let's see if I can't light it again with the lighter. All right. It's still pretty hot, so it lights up pretty quick. Let's see if it works with the pencil. Okay, great. So if you don't have a kebab stick, give it a shot with the pencil and see if you can't get this thing to spin. That's the goal. Ah! Don't burn down your house. That's also the goal. I have one last design. I'm going to try and cut this real quick.
Okay, so I've successfully cut it. I find that using the front 1/4 inch of the scissors is the best to deal with the odd way that cutting aluminum foil, it behaves differently than paper. But so now I'm going to try and lay it flat and flatten it back down a little bit without messing it up, which I kind of did just then. But very good. Got it nice and flat. And I guess I'll slide it and use my finger here. I need a slight point. So you might use like another pencil maybe. A duller pencil can kind of give you a better shape. Ah! Alright, here we go. Let's see, is it too long? It might be too long. Oh yeah, that's way too long. So let's take a quick peek at what it looks like from the side. So it's way too long, it's going to hit the flame, so I'm going to go ahead and cut a good portion of it right off. There we go. Now I got a problem up here. It's not very... There's too much... Ah, we're burning down here. Oh, it's getting stuck in the wax. I don't know if you can see it. Camera on fire. Ah, so I'm going to cut. There we go. Oh, nice. Okay. So now we're kind of in business. This is getting wrapped up. I'm going to just readjust there. And then I'll give it a little nudge. Nice. And there you go with the pencil. And let's rotate it. Clear the background a bit. For more drama. Anyway, good luck. It's really... That's actually not even a very good one right there. It's getting caught. Very inefficient. Too much turbulence. Can you make one that spins continuously without fluttering like mine is? That's the challenge. Good luck.
All right, so finally we'll look at radiation, which is energy that is radiated or transmitted through the electromagnetic field. And we have a graph here that shows you how much energy or power each of these waves have. And you see microwaves are low powered, and you get up to infrared, which is more powerful, and then you can see where light falls onto that scale. And here I have two different jars, one of them a reflective aluminum and one of them black, which absorbs all the frequencies of light. And so it gets hotter faster. And we pull out the thermometer and you can see that indeed the black container retained more heat. It absorbed more thermal heat. So if you wear a black shirt out in the sun in the summer, it's going to heat you up more than if you were to wear a white shirt or something that reflected the heat. And another example of thermal energy and color is to think about snow and why you get ice caps. Ice caps reflect most of the sunlight, so sometimes ice can last a long time on the sidewalk if it's reflecting the light of the sun. But in places like the poles, you get glaciers which never melt, even with light. And so they're reflecting most of the energy. All right, so real quick, a review. Sitting next to a fire, you can experience all three forms of heat transfer. Convection, which is the heat rising above the fire, and you can warm your hands over it, or you can cook a hot dog over it. Conduction is if you were to place a metal pole into the fire like a poker. The pole itself, the metal pole, would become hot and you could feel that into your hand. Or you can feel the radiation and see the light of the fire as you sit next to it in the dark. You'll see the light. That's one form of heat energy. And then you can feel the radiation in your hands by just holding them up to the fire to warm them up. When attempting to melt copper in a backyard furnace or keep a cup of coffee hot, thermal transfer can be a pain and you try to prevent it. But in other cases, it's useful. For example, when we cook food, we use all three forms of thermal energy transfer to do that, and we'll look at each one of those. When you boil water and boil an egg or cook noodles in that water, you're using conduction. The heat goes directly into the pan, and the pan transfers the heat directly into the water, and the water transfers it directly into the food. When you use an oven, you're using convection because the heat is flowing through the air in the oven. And so you don't want to be opening it a lot because you're releasing a lot of the air, but it'll cook the food in the air as it circulates. And that can be difficult in Colorado because the pressure isn't high enough to get that heat deep into the food you're cooking. And so sometimes you can burn the outside while leaving the inside not fully cooked, and that has to do with the pressure of living high in the altitude that we're at. Finally, you use radiation when you use a microwave oven, which generates microwaves, and those microwaves shoot into the food and literally vibrate the molecules in the food, the water molecules specifically. And so if you put metal in there, you get a fire reaction. But if you put food in or anything with water, the water will start to vibrate, and that heats up your food. And that's how you can cook using radiation in a microwave so much faster than, say, a convection oven or through conduction even. Phew, that was a long lesson. And we're back at the cup of coffee, and it's almost gone, and it's cold. But I'm still going to finish it up. Thanks for joining me today as we learned about entropy.